Volumes of other cross-sections, Part 3. We're going to do a couple examples, finding volumes of other cross-sections, where the cross-sections are perpendicular to the y-axis. So in this first example, let's take a look at this region, bounded by the x-axis and the function f of x equals 4 minus x squared. Let's find these intersection points. We can guess and check these pretty easily, or simply set the function equal to 0 and see that the intersection points are x equals negative 2 and x equals positive 2. Now, let's draw one of our cross sections perpendicular to the y-axis, which will have a small width of dy. And note that the cross sections coming out of the screen are going to be rectangles whose height is twice the base. That is h equals 2b. Recall that if we have dy, everything should be y. So let's find this top y limit, which of course is y equals 4. Based on my function, I know that f of x is 4 or less. Let's turn our function into a function of y. So right now I have y is 4 minus x squared, which gives us x squared equals 4 minus y, or x equals, and be careful here, plus or minus the square root of 4 minus y. Where the right side over here is the positive square root, and the left side is the negative square root. The length of my base is going to be the big value over here minus the small value over here. So it will be the positive square root minus the negative square root. And if we were to simplify that, that becomes 2 times the square root of 4 minus y. So our volume of one of the rectangular cross sections with the width of dy is base times height times dy, or our base times 2 of those bases times dy, which will simplify to 4 times 4 minus y dy. 4 because 2 times 2, and 4 minus y because I have base times base over there. Which means the entire volume is when we sum all of these pieces together, starting at our lower y value 0 and ending at our upper y value 4. Let's finish off the algebra of this. I will rewrite it one time before I take the antiderivative. And now we can take the antiderivative. So 16 becomes 16y, and then minus the antiderivative of 4y is 2y squared from 0 to 4. Plug in our top limit, 16 times 4 minus 2 times 4 squared. There's your top limit. Minus plug in our bottom limit, which is 0. And we get to the volume of these cross sections, all added together equals 32. Let's do another example. And this one will have an advanced integration technique. So if you don't know this technique yet, don't worry about it. I will show this in a later video. Or you might have already learned it, depending on how the professor teaches your class. So this example, let's look at the region bounded by the y-axis. On the right by the graph of f of x equals e to the x squared, and above by the horizontal line y equals e. Cross sections, in this case, perpendicular to the y-axis. So let's draw a cross section with the width of dy. Coming out of your screen will be squares. So I know that the volume of one of these shapes will be b squared times dy. So I'm missing the length of my cross section, or the length of that base. Since I have dy, I know everything should be in y's, including my function. So let's turn our function y equals e to the x squared into a function x of y. That is, x equals some function of y. To cancel out the e, we will take the natural log of both sides. And then we end up with x equals the square root of the natural log of y. The positive square root, because I have only the positive square root over there. That means the volume will be the sum of these cross sections, starting at, what is the lower y value? Well, when x equals 0, and let's go back up to this one. When x equals 0, y equals 1. So our lower limit is 1. Our upper limit is given, it's e. And then the length of our base is exactly the square root of natural log of y. Minus 0 if you want to, but it's really not necessary. So base squared becomes natural log of y. So if you have not learned integration by parts, this is about as far as you could go, or you could use a calculator to get an answer. But we will use integration by parts to solve this one. So integration by parts is when we have the integral of u dv equals uv minus the integral of v du, where we know u and dv, or more specifically, we can choose something to be u, and then everything left over will be dv. In this case, I will choose u to equal the natural log of y, which means dv is what's left over, and the only thing left over is dy. Notice that to solve, I need v as well as du, so let's find those. If dv is dy, then v is y. We don't need the plus c at this point. If u is the natural log of y, then du is 1 over y dy. And then we can plug in the natural log of y dy equals u times v, and I'll rewrite it as v times u just because I like it this way a little bit better, minus the integral of v times du, which is just dy. And I'll put the limits on at the end. So the integral of natural log dy equals y times natural log of y minus y. And now let me go back and put my limits. So I can put my limits down here as well. Plugging in the top limit, we get e times the natural log of e minus e. Plugging in the lower limit, I get 1 times the natural log of 1 minus 1, which simplifies down to 1. So the volume of these cross sections, which are squares perpendicular to the y-axis, from y equals 1 to y equals e, is 1.